All right, so let's wrap up this chapter with elastic potential energy and Hooke's law. Now, Hooke's law says that the force from a spring is proportional to the displacement or the compression of the spring. Either the displacement or the compression of the spring. That is, how much do you stretch it or how much do you compress it? It's given in this way, that the force is equal to negative K times X. So if I imagine a spring here hanging, let's say that the equilibrium position of this spring is right here. So I have stretched this spring by a distance of X. In fact, I've stretched it by a distance of negative X, because if this is the equilibrium position, then that is X equals 0. All right, so I stretched it by a distance of negative X, and so I can calculate then the force is going to be negative Kx. More about K in just a second, but that's going to be a negative K times a negative X, which is going to be a positive number. The two negatives will go away. And we can see by the force, like this string is going to want to return back to that equilibrium position. So there is an upward force. So that's where this negative comes in right here, is that the force is opposite the direction of the displacement of the spring. So if it's stretched in a negative direction, the spring's force is going to be in a positive direction. If the spring is stretched in a negative direction, or excuse me, if it's stretched in a positive direction, then the spring's force is going to be in the negative direction. Now, K is the spring constant. It's measured in Newton meters. It's determined experimentally. If you're in the lab, we'll do this, where we actually determine the spring constant of a spring, and you just simply measure the force and the length, and you measure the slope of this line, and that gives you the spring constant K. Purely an experimental value. So let's say I have this spring, this object on a spring. In this case, it's horizontal. These are all the forces that I have acting on the spring. I have the force due to the spring here, my normal force, my weight, and my kinetic friction if there's friction. My velocity in this case, since my is going to be to the left, and my equilibrium position is there. So notice, as we've already said, how the force from the spring is always opposite the displacement. So anytime the spring is stretched beyond this point, the force is always going to be in that direction. And anytime the spring is stretched beyond or compressed to that side of that point of the equilibrium position, the force is always going to be in that direction. The spring simply, you can think of it that it wants to return to its equilibrium position. Sort of a very Aristotelian idea, that it wants to return to this resting position. It has this restorative force, this restoring force. There will be a clip on Moodle. You can listen to it. This is just about the history of Hooke and Newton. Sometimes forget that Hooke and Newton and Boyle and a number of other scientists, really the first scientists, were all part of the Royal Society in England. And this is a clip about the history of that. I'll post it on Moodle for you to listen to. Now, if we have a scenario where we have energy involved, we can say, just as we did before, that the kinetic energy plus the potential energy initial is equal to the kinetic energy plus the potential energy final. This is just our conservation of energy, and this is true still for springs, although in this case, our potential energy is not going to be gravitational potential energy, but it's going to be elastic potential energy. So let's just look at these three scenarios. Here, where the spring is not compressed and it's not moving, they're both equal to 0. Now, when I compress the spring by a certain value x, I can calculate the potential energy. And the elastic potential energy, the potential energy of the spring, is equal to 1/2 kx squared. This comes about when you actually integrate over fx, which we won't do in this class, but we'll do in the calculus place class. So the potential energy is equal to 1/2 kx squared. Now, when it's fully compressed, all the energy is in potential energy, right? But the kinetic energy is 0. So when the spring is fully compressed as it's moving back and forth, my velocity over at this point is going to equal 0. And then when it comes back When the spring is no longer fully compressed, but it is fully extended, then the spring potential energy is 0, and the kinetic energy is equal to 1/2 mv squared. So more correct to draw my block here, that the potential energy at x equals 0 is equal to 0, and the kinetic energy is equal to 1/2 mv squared. I can show you quickly how to derive this. You're not responsible for this, but the potential energy of a spring is equal to the negative of the work done. So any work that I do, the negative of that is the potential energy, and that's equal to the integral of negative f dx, and the integral of kx dx, which is, if you're in calculus, so this is 1/2 kx squared. All right, there's a quick test. You can try that out. There are also several homework questions and also some old test questions. Now, just one last thing, which is power. Power is the rate at which energy is transferred or work is done. Power, we'll call capital P, is just equal to work over time, or you can think of it as energy over time. It has units of joules per second, but 1 joule per second is called 1 watt, right, named after the scientist Watt. That comes up in the homework a couple of times. You just need to know what power is, that it's work over time. There's an alternate thing. This comes up in the homework once. Since power is equal to work over time, and work is force times displacement over time, then I can rewrite this as F times V. So this is an alternate expression for power. It's the force times the velocity of the object. The force is pushing on it and the velocity of the object. Again, that comes up in the homework just a bit. It's sort of a small part of a problem. That's the end of chapter 5. Please complete the homework and be working on those old exams and complete the quiz. I'll post the date soon.